When we use multiplexer, a term called multiplexer tree always arises because sometimes we want to implement more than a higher function of a multiplexer, but we may have a lower capacity multiplexer modules. For instance, we assume we want a function that requires an 8 by 1 multiplexer, an 8 line to 1 line multiplexer, and we only have at our disposal 4 by 1 or 4 line to 1 line multiplexers. At that point, we would need two 4 line to 1 line multiplexers to implement our higher order multiplexer function, and that is when we talk about multiplexer trees. So an example is illustrated by this diagram, whereby we are able to form a higher order multiplexer function using two lower order multiplexers. In this case, we have 4 by 1 multiplexer combined with another 4 by 1 multiplexer, and we get an 8 by 1 multiplexer. Sometimes we may use 4 to 1 or 4 by 1, but I think the correct way of writing this expression should be 4 by 1, and I think we will use 4 by 1 when you are talking about decoders. So for now, I think we will stick with this notation of using the times to represent the ratio of input to output. So the best way to illustrate the use of a multiplexer tree is by using an example. Then we are told to implement a 16 line to 1 line multiplexer using 4 line to 1 line multiplexers. So that is another complex example of a multiplexer tree, but it is something doable whereby we want to achieve a higher order multiplexer function, and yet we have sufficient or adequate low order multiplexers. So how would we do this? The first step is to know for a 16 line to 1 line multiplexer, how many inputs are these? We can clearly see that the number of inputs are 16, and we are able to express our input lines as 2 power n, where n is the number of select lines, and therefore we can see here that the number of select lines are going to be 4, because 2 to the power 4 will give us a 16. So once we have known that we need 4 number of select lines, the next question that we ask ourselves is how many select lines do we have at our disposal? And what we know is that we have each multiplexer, which is a 4 by 1 multiplexer, has a maximum of 2 select lines, and therefore we cannot use these 2 because we need 4. So one of the intuitive way of doing this is then using the 4 inputs of one multiplexer, and that becomes our select lines. So how do we end up now with our final design? Our design therefore says that we will need 4 multiplexers to achieve our 16 input lines, and we'll need 1 additional multiplexer to serve as our 4 select lines. Therefore, this totals to 5 multiplexers of 4 by 1. This should allow us to achieve our 16 by 1 multiplexer function. Therefore, the next question should be, how do we arrange these 4 multiplexers and 1 demultiplexer? And here is a very simple idea that we should have our least significant bits, the first 4 least significant bits entering into first multiplexer, and the 4 most significant bits entering into our multiplexer 4. This is multiplexer 1, we will have multiplexer 2 there and multiplexer 3 there. So this should be our I0, I1, I2 and I3, and the last 4 most significant bits should be I15, I14, I13 and I12. So what we normally do in this case is that we will combine the select lines of the first 2 multiplexers and the select lines of the last 2 multiplexers, and the output lines from each of these multiplexers will become the input of the fifth multiplexer. And what we will do next is to say that because we have 4 select lines, or S3, S2, S1, and S0, what we do here is that the first or the 2 most significant bits are going to be used to control the multiplexers. So if we now look at this diagram, what we see is the same design, probably in a better organized format, that we have the most significant bits. The uppermost 4 significant bits are represented by multiplexer 4, and the second 4 most significant bits are inputs to multiplexer 3. The lowest or the least significant 4 bits are the inputs to multiplexer 1, and the second lowest significant bits are inputs to multiplexer 2. And what we observe is that it has 5 multiplexers. 4 act as the input lines, and 1 selects the output from each of 4 multiplexers, so that we have Y0 there, Y1, Y2, and Y3. Those 4 outputs enter our 5th multiplexer, and the 5th multiplexer is selected by 2 select lines, S3 and S2. And what we get, how we select the inputs to each of the 4 multiplexers is setting a parallel select line, the most significant being S1 and S0 being the least significant. So how do we understand what happens? For instance, we want to select I3. I3 is clearly in the first multiplexer. So what we will do is we simply want to send a code to our 4 select lines as 0011. So what we know is that the most significant bits, S3 and S2, are 00, and for that reason Y0 is selected. So we know that whenever we have selected S00, our input, which is now equivalent to Y0 and is our I0, is selected. And what is coming out of Y0? We know that the select lines are S1 and S0, and we know that for 3, S1 and S0 are at 1, 1. For that reason, we sent a 1 here and a 1 here, and therefore when we have sent a 1, 1, then the code is a 3, and therefore what is selected is this input I3. Let's look at another example. For instance, we want to select output or input I11. So I11 is going to be represented by 1, 0, 1, 1. This is 8 plus 2 plus 1. That becomes 11. Therefore, if that is the code we are going to send to our 4 select lines, S3, S2, S1, and S0, the 2 most significant bits will go to our 5th multiplexer, and here we get a 1, 0. And a 1, 0 selects input line 2, which is our input line 2 is Y2. And therefore Y2 is coming from this multiplexer 2. Therefore we have narrowed our number of input lines from the 16 that we had to only the 4. And therefore what goes to the S1 and S0 is 1, 1. Again, we are sending 1, 1 to S1 and S0, and therefore the I3, this is equivalent to a 3, and therefore I3 is represented by the most significant input, which is I11. And for that reason, we are able to select input line I11 as required. So this is the basic functionality of multiplexer tree, that is using 4-line multiplexers to implement a 16-line multiplexer, that it is indeed working as it should. And we have seen with 2 examples of I3 and I11 that indeed it does work. So the next thing we would need to look at is the truth table of this select line. Now that we have 4 inputs, we clearly see that when we want to select input 11, we are setting an 11, just like we have seen, and now we have seen that the output will be I11 because the first two select lines go to select the outputs of our fifth multiplexer, and the two least significant bits are used to select the inputs of our four multiplexers. So with this table we have seen and we have verified that whenever we need to select any of the inputs, we just need to set our normal code, and in fact we are getting the output as required.